Okay, so let us continue the lecture on Gromov-Witten classes. So we discussed this much. So we discussed that we were looking at genus 0 pointed stable curves, stable maps in P2 with 2 times class of P1. So we discussed the interior, the non-singular conics, and the boundary of it, boundary of this compactification, 2 times class of P1. And we discussed that there are non-singular conics sitting here. Non-singular conics are sitting here. There is also normal crossing singular varieties, intersecting lines also sitting in here. This is a subset of P2. Yes, there's a third possibility also. So if I have a map from a curve to P2 such that image of this map, so this, need to specify the data of point of intersection of two lines, data of point of intersection of two lines. Okay, so this is this thing, this point of intersection, and as you can see, this point of intersection moves on a P1. So really it's a point and it moves on a P1. So this is the data of a point moving on a P1. Okay, so that's those maps. And then we have another case also. We also have maps like this, maps from P1 to a line in P2 such that this mapping is 2-to-1 cover of this line on P2. So given by 2-to-1 branch covering of degree 2 over L, the line on P1. Okay, so if these are the non-singular conics, if we want to identify these kind of things, the possibilities are basically location of this point of intersection. So that's a P1 worth of choices. How about that one? That also, you need to basically specify the location of the branching points. So, right, so those are determined, these are determined by specifying the line, of course, the line over which you are branching, right, with 2 branch points, 2 branch points. Okay, so as a whole, therefore, this compactification of the moduli space of a stable maps genus 0 marked points to P2 with homology class 2 times class of P1 which is P2 2 times P1 plus the boundary P2 2 times P1, and that is non-singular conics sent to P2 plus normal crossing of lines sent in P2 plus branch coverings, 2-to-1 branch coverings of lines sent in P2. This moduli of such things is a P1 with a P1, because this point of intersection can move on P to P1. And the moduli of these things is also a P1, but choice of 2 branching points on it. So, unlike that. Okay? And so this thing is actually a second symmetric product of P1. But then you need to smoothen it because it's possible that these 2 points actually lie on top of each other. All right. And this is as a whole just the space of conics. As a whole, this is the classical space of conics. Space of conics. All the possibilities. Okay, so this is end of that example. Last part of that example. This is the thing that we missed out because then I didn't have time. So, okay. All right, so this was an example. Now let us continue. Here's the definition. Let X be a complete non-singular variety with tangent bundle T of X. Okay. Then X is called to be convex variety. Okay, convexity. If for any morphism mu from a P1 rational genus 0 curve to X, right? H1 of P1 pullback of tangent bundle of X is equal to 0. Okay. So on P1, by Kodara vanishing, you cannot have H2 and stuff. You can have H0 of a sheaf and H1 of a sheaf. If you don't have any Hierarch homologies for pullback of the tangent bundle, variety itself is called convex. Okay, so what are the examples of convex varieties? So example, convex varieties, you can show that homogeneous spaces like spaces like G modulo P, where G is a Lie group, and P in G is a parabolic subgroup. So this is a convex variety. Here is a convex variety. Here, since is acting transitively on X is the quotient, and X given by G mod P Then okay, since G is acting on that, then oops, T of X is generated by global sections, and hence mu up star of T of X is globally generated on P1. If something is globally generated, the abstraction for it to be globally generated is 0. And this is the abstraction for the pullback of the tangent bundle to be globally generated. Globally generated means it has H0. And there is no H1. So if H1 vanishes, it's always just it has H0, non-trivial H0, and that's globally generation. Okay, hence for any morphism, hence for any mu from P1 to tangent bundle, you have that if I take if I take H1 over P1 of the pullback of the tangent bundle, it's going to vanish. Now, okay, fine, this is just an example, but the main theorem is really the following. Let X be a projective, non-singular, convex variety that satisfies this condition, then the following statement holds true. Then the following statements hold true. One is that M0n x beta moduli space of non-singular maps from genus 0 curves with endpoints on them with homology class beta is a normal projective variety of pure dimension. It is equal to dimension of X plus this number, first term class of X evaluated with beta plus n minus 3. So beta is a homology class. This really notation really means you're intersecting this with beta. Beta is element of H2 of X in Z, and C1 is a codimension 1 class, and it's codimension 2 real. So this lives in H upper 2 of X with Z. So if you collapse them together, take the intersection, you get a number. Okay. Normal. So normal here. Normal. Okay, I know that you know it. It's defined in books and so on, in the Hartshorne also, but here maybe normal means that local ring of variety at every point. Every point is integrally closed domain. So this moduli space is a normal variety. All right, this is statement about M0n for a convex variety, if I have a convex variety. And then there are other statements too. So if I compactify it, I can say more. So part 2 is that M bar 0n x beta, if x is convex non-singular projective, is locally a quotient, of a non-singular variety by a finite group. Okay, so it has orbifold structure. And 3, M star 0n x beta, which is the open locus of stable maps with no autos, with no non-trivial autos. Because we used star as the interior open locus, maybe I call this something else. Maybe call it 0, with 0 automorphisms, okay? M0 and x beta is a non-singular fine moduli space with the universal family. The part that doesn't have any non-trivial autos is a fine moduli space. But it's non-singular. And you will see soon the reason this thing is overall kind of non-singular. So the reason is because you will see when we discuss the singularity of the moduli space of stable maps, you will see that the part of what is capturing the singularity is exactly the cohomology of pullback of the tangent bundle of X. That's what it is. You will see that. And then you realize that when the variety is convex, when you look at the deformation space at every point of the moduli space, that's a vector space. As you vary over points in the moduli space, this deformation space not only glues flatly, it becomes a bundle. And the obstruction for it to become a bundle vanishes. Therefore, the tangent bundle of the moduli space is defined everywhere. And if the deformation sheaf, we're going to work with sheaves, deformation sheaf is globally, remaining globally as a locally free sheaf, as a bundle, that means that this space is smooth. This is the definition of a smoothness in algebraic geometry. That the deformation sheaf gives you a bundle globally over the whole space. If you have an obstruction to that, that's basically telling you that the moduli space for some reason is non-smooth. Whether it has multi-components or it has singular points or loci. So this condition guarantees that on this moduli space, the deformation sheaf becomes a bundle. This is smooth. Okay. All right, so that's that. So this is an example of non-singular smooth moduli spaces for convex varieties. So we would like to consider more exciting cases of stable maps. So let us talk about Gromov-Witten classes. Witten classes. So the diagram that you would like to have in mind is the following diagram. You have the moduli space, compactification of the moduli space of genus G stable maps with n mark points on them with homology class beta. So that's the moduli space we've been discussing about, stable map moduli space. Then there is a map from here to x to the n. That's your variety times itself n times. And then there is a map from here to, so this is, I'm going to call pi 1. Then there's a map from here to moduli space of genus G n-pointed stable curves. So I forget the map. What is the map pi 1? The map pi 1 is the following. Given a stable map, f from configuration of a curve with n markings on it to ambient x, you can ask yourself, what's the location of these pi's? So we get a well-defined tuple f of p1, f of p2, f of pn, and this belongs to x to the n. So as soon as you give me a point in here, via this evaluation map, I land on this space. So that's pi 1. Okay? Remark, pi 1 can be shown to be a morphism. Okay. What is pi 2? Now, pi 2 is more involved. Pi 2 is exactly the thing that we discussed before. In the interior of this moduli space, you're looking at non-singular curves, and you map them. Pi 2 is the map morphism that forgets the mapping. So you just forget and go down. As long as this thing is smooth with n mark points. Oh, something happened, by the way. Oh no, it's okay, right? It's all right. Someone is, yeah. As long as this thing is in the interior and is smooth, you just forget the map and there's no problem. But on the very boundary, here you're looking at interaction between stable maps versus stable curves. It is possible to have a stable map. We discussed what is the stable map. You have a curve with n markings. This curve could be reducible. Its irreducible components could be genus 0, genus 1, or higher. If it is genus 0, how many options do you have? Either your map is non-constant, in which case you know exactly where it goes, it's fine, or constant. If it is constant, because you can dilate the curve by multiplication by constants and post-compose with the map, you will get infinitely many possible maps because the map is constant. Doesn't matter. That's not good. So if the map is constant, okay, so it's not rigidified on the map side, you would like to rigidify the domain of the map. So you put at least 3 points on it. Okay, genus 1. Well, you have two options. Either the map is non-constant, in which case you're fine. That's finite automorphism. Or it is constant. If it is constant, then again, you don't like to allow dilations. So you put at least 1 point on the genus 1 component. That fixes the map. You cannot, even if you post-compose, you will get finitely possibilities. All right, so as you can see, you are left with this situation where you have non-constant maps from genus 0 or genus 1 components, and these genus 0, genus 1 components on their own, a priori, can have infinitely many automorphisms. The fact that map is non-constant tells you that the whole system together with the map is finite automorphism. So when you forget the map, these things do not have that non-constant map anymore, and they become unstable. So as you go down to this component, you need to collapse them. Otherwise, you land on unstable curves. So this map is non-trivial. In the interior of the moduli space, it's just an honest forgetful map, no problem. But on the exterior, where you're sending stable maps to stable curves, after forgetting the map, you need to collapse unstable pieces of that curve. Okay, so this is that forgetful map. Okay, so this is kind of very important. So let's say it again one more time. If f from C to X is a stable map, then C need not be stable. Be stable. Yes, we know that. We know the recipe, what makes this stable. However, if n plus 2g is bigger than equal to 0, then this 3, then successive contraction of unstable components of C gives us a stable curve. Let's call it C tilde. Then one can say that pi 2 is the map from isomorphism classes of maps from C to P1, C and P1, Pn to X to isomorphism class of C tildes. This is also isomorphism class of this thing. Moduli space parameterizes points in the moduli space are up to isomorphism. So these are isomorphism classes. So this sends this from here to isomorphism classes of the stabilization of the unstable curve, which you obtain after forgetting the map. Okay, so it's not that bad, right? If we know exactly which thing is, we don't get confused. You see that this makes sense. Okay. All right. Okay, so that's the two morphisms. And in order to I always like something that I've realized. I wish that all my teachers do that. Many of them did that. Okay, is that when you're trying to convey a concept, tell me the end of the story maybe earlier so that I know where we are going. Okay, so here's where we are going. I'm going to define a class. I'm going to call it Gromov-Witten class. This class is a homology class, for instance. I'm going to pull back something from here and push it down there. So it's just ladder construction. Cap construction, hat construction. Goes back, comes down. That's what it is. So these are the ingredients. In order to define this class, I'm going to look at this diagram. Okay? So that's that. Okay, so this is that. All right. Remark, pi 2 can be chosen. Pi 2 can be, no, not chosen, can be seen to be a morphism. Can be seen to be a morphism using techniques of Knudsen. Anyway, now we are not going to discuss it. Now assume X is a smooth, projective, and convex. So its tangent bundle is globally generated even after being pulled back to P1 for any morphism from P1 to X. Okay, then M bar Gn X beta is an orbifold. An orbifold, we discussed it, is an orbifold of expected dimension, expected dimension 1 minus G times dimension of X minus 3 minus integral of canonical bundle of X over beta plus N. That's some result. And what is this thing, by the way? This expected dimension really is the dimension of H0 of tangent bundle of M bar Gn X beta minus dimension of H1 of tangent bundle, tangent sheaf M bar Gn X beta. Dimension of H0 of it minus H1 of it. Okay. Now you would say, I thought you said it's a smooth. It was a smooth for genus 0 pieces. So when you go higher in genus, tangent sheaf of the moduli space fails to be always locally free. And it would have higher cohomologies. And this dimension of H0 minus H1 is actually the expected dimension of this space. This is a very classical thing. You have a space, variety, and its dimension doesn't stay, it's singular, for instance, it's singular. How do you define the notion of expected dimension? For instance, something like this. Well, you look at the deformation space, tangent bundle, right? This thing at every point gives me one directional tangent vector. So it's a C. Its dimension, its deformation space is always one dimensional, except as at this point, right? So the deformation space of this thing does not stay as I roam around the space. Does not space flat because at some point its dimension goes down or goes up, all right, jumps. So this tangent sheaf that you define, the sheaf is something that over every point of the space gives you this tangent space. This sheaf will not be locally free, and it will have higher cohomologies. If the space is like this, you will get exactly what the non-smoothness tells you, that there is some piece in here, and you can calculate this dimension. Now, this piece tells you what does it take for tangent sheaf to be globally generated, or a vector bundle. Okay, so normally you have this space, so you look at H1, H0 of tangent, right? This is a space, right? And then you look at this one, H1 of tangent. All right, and then this is a map. You look at the 0 point in here, and you look at the pre-image of 0 under this map. Let's call it F. You look at the F inverse of 0, and it actually is a subspace inside here. Now, this subspace is the realization of the part of your space for which tangent bundle, tangent sheaf can be a bundle. Do you know why? Because these are all parts of H0 of Tx for which H1 vanishes. It's the pre-image of 0. So this part that sits inside here is the realization of your space, the locus of the space that has expected dimension. Okay? That's what it is. That's the expected dimension, what it means, really. Okay? As the obstructions vanish, your space is fine. So there is a locus inside the space that the obstructions vanish. Okay, so that's the expected definition of expected dimension. And here K of X is the canonical class of X. canonical class volume form, canonical bundle, canonical class of X. And yeah, expected dimension, I already mentioned it. Okay. Okay. So you see, we never like to work with the spaces. We would like to work with parts of the space which are almost nicely behaving and at least kind of somehow nice and smooth, right? At least our tangent sheaf behaves nicely on them. So if I look at the fundamental class of this space, it's a class in the homology theory of my space. And this fundamental class, you can imagine, is ill-defined, right? Because at some points in this space, the degree of this class jumps down or up. The fact that the tangent sheaf of this space has fibers which are jumping in dimension tells you the inhomogeneity in behavior of this space. The fundamental class also measures that, right? So I'm not going to like that. I cannot work with that, right? Because my space becomes singular and I don't want to use that. So instead, I will produce a class which I hope can stay constant as I roam around on my space. And that class is going to be the homology class of the part of my space which is of expected dimension. And over there, everything is kind of nice. Things do not jump in dimension. Okay, I cannot do a calculation for the whole space, but for that locus of the space, I can. So for that locus of the space, I'm going to construct a homology class similar to fundamental class. And that one is artificial and virtual, and I call it virtual fundamental class. So the virtual fundamental class of a space is a homology class associated to the space, and it sits in a certain degree of homology theory of my space. What is that degree? It's the expected dimension of my space. And it's not going to leave that chamber of homology theory. Homology ring of a space is a graded ring. It's graded by the degree, by the dimension. It's not going to leave that. Even if as I roam space over a space, it's not going to leave it. It's going to stay invariant, because it's now eliminated possibilities of things like this. It's in the preimage of 0 inside here. So we will discuss this thing. It's more involved than that, but I'm just kind of trying to give you some kind of intuition behind what is the virtual fundamental class. So studying of deformation abstraction theory of a space allows me to construct this class virtually on my space. That's why the ingredient to construct a virtual fundamental cycle is something called deformation abstraction complex. We will do it both for Gromov-Witten theory and for sheaf theory, Donaldson-Thomas theory. We will construct virtual fundamental class. Okay, so we get this induced map. So now consider pi 1 and pi 2. Pi 1 and pi 2. I'm going to define a pullback map, pi 1 upper star, from H cohomology theory of X with rational coefficients n times. N times. To cohomology theory. Okay, so pullback should take me from cohomology to cohomology to cohomology theory of m bar gn x beta with rational coefficients. Okay. Furthermore, consider pi 2. Furthermore, we get induced map pi 2 lower star pi 2 lower star, which I'm going to define from homology theory of m bar gn x beta with rational coefficients to homology theory of m bar gn with rational coefficients. Okay. Here we are still assuming that n plus 2g is bigger than 3. Okay. All right. So that's that. Since all the spaces involved are orbifolds, okay, they have orbifold structure, non-singular, but it has orbifold structure, then Poincare duality and pi 2 lower star induce Gisin push forward map. Okay. Well, otherwise you cannot have Poincare duality. If it does, the space should have at least this minimum orbifold structure. Okay, so what is that? It is going to be pi 2 lower Schrick from H homology theory of m bar gn x beta with rational coefficients to H 2m plus star of m bar gn with rational coefficients, where m is equal to g minus 1 times dimension of x plus an intersection of canonical bundle, canonical class with beta. So when n plus 2g is bigger than 3, pulling something back from here and Gisin push forward it to here, and Gisin map, I encourage you to search in the internet. Gisin push forward and pull back map, Gisin map. Also look at the book of Fulton if you like, or EGA7, SGA7. So for this, Fulton's book on intersection theory, best source really. Intersection theory 7, very good. I mean, all right. So I'm going to write it down also. So you get the pull back and then push forward via Gisin map. So you will get when n plus 2g is bigger than or equal to 3, we obtain the Gromov-Witten class. It's a class. It's a communication between cohomology theory here, homology theory here. Gisin pullback, okay, Gisin push forward is nothing really fancy. You're pulling back cohomology class to here. You end in the cohomology theory in here. But then the push forward of this morphism is well defined for the homology. So Gisin actually does induce what happens for cohomology. But at some point, you need to apply Poincare duality. And for when you apply Poincare duality, you dualize classes. You need to have orbifold structure at least. When the X is non-singular projective convex variety, this one has orbifold structure. So Poincare duality is well defined for such spaces. So you can dualize. And then you can push forward that cohomology class. As you dualize, dimension of the ambient space needs to matter, right? So this is a homology, and you're taking that element of homology, h lower I, to h n minus I, or m minus I. M is the dimension of the ambient space. And this is that, the expected dimension. But it's in real dimension, so 2 times that. This is the complex dimension, complex expected dimension of that space. 2 times that's the real expected dimension of the space, so you get something like that. Okay, so then you push forward, and it's becoming well defined. So then this gives you literally Gromov-Witten class. So what is it? It's a class I'm going to call I. It depends on the genus of the curves. It depends on how many points on the curves there is. It depends on homology class of the curve, because it depends on these spaces. And it depends on tuple of n elements. And these n elements are members of cohomology of X with rational coefficients times n. N cohomology classes. And what is that? It's defined as pi 2 lower star of pi 1 upper star of alpha 1 times alpha 2 times alpha n. That's it. Okay? I want to okay? Good. So, all right. So how do I want to define it for you? Let me see. Maybe I should just do it in here. Okay. So I want to see, should I do it now? Good question. You pick n cohomology classes on your variety X. Okay? And then you have a morphism. There are n cohomology classes in here. You tensor them n times, pull back, push forward. That defines for you Gromov-Witten class. It depends on this space, so it depends on G, it depends on N, it depends on beta, it depends on choice of cohomology class. Definition. Okay? Later question is, what does it mean? Can you tell me? What is that? What is that class really? What are we doing? That's a better question. But I would like to. Go ahead. Very, very good. Intersection of curves in what sense? With what? Intersection of curve with what? Let me tell you one thing. I give you a hint. This class is yes. This class as a whole, IG and beta, alpha 1 to alpha n, okay, is a class in cohomology theory of M bar Gn. Lives in here, cohomology theory of M bar Gn, appropriate degree with rational coefficients. M bar Gn itself has a fundamental class or a virtual class. If I take this element and intersect it with that homology class, I will literally get an invariant. Question is, what is that invariant counting? But you're very much on the right track. You're almost like a Gromov-Witten theorist right now. What is it? Tell me. What is your guess? What does it count, this Gromov-Witten invariant? Relate this Gromov-Witten invariant to the choice of n cohomology classes in X. That's what we are trying to do. He asked, is this choice of alpha having anything to do with mark points? I said, yeah, it does. But you choose n classes. Pull back, push forward. And then I'm saying the relation has to do with, can you tell what the meaning of this class really is? Excellent. The stable curves that pass through these points. Good. Which points? Where are the points? Where are the points? What's the communication between points and these classes? I want to go to a city, and I want to make sure that I definitely meet 3 locations in this city. First thing I would ask, someone says, you go to this city, and you need to go to the such mall, shopping mall, to buy a leather jacket, and you need to go to a hospital to get a COVID vaccine, and you need to go to University of Miami to teach. Okay. Or some university to teach, not University of Miami. What would you ask if a person asks you to do that? It's 3 tasks you have to do. Go there, you have a pin over there, you have a pin over there, and you have a pin over there. First thing you ask is, give me the address, right? Which hospital? Give me the address. Which university? Give me the address. Which shopping mall? Give me the address. The cohomology classes give you the address of loci in X, where these mark points must meet. Okay? So this construction tells you that you have a curve inside X with n markings, and you're in some sense cohomologically giving the address of where the mark points are. You remember you are trying to pin it, right? Where should be the pins? The pins should lie on certain subvarieties of X. Those subvarieties have homology class or cohomology class. Give me the address, and I construct some class. This class is the representative of all curves which are chosen from here, which in here meet exactly those subvarieties with cohomology class alpha 1, alpha 2, alpha n in X. Okay, so that's the meaning. This is the cohomology class of the locus of that moduli space, parameterizing all possible curves that meet those loci in X. Good, very good question. Yeah, thank you. Okay, so let us continue, and I will spell it out for you, because I think this is the most important thing, really. First of all, yeah, so what am I gonna do? This precisely gives the cohomology homology class of set of curves in X, f from CP1 Pn to X, such that push forward of the curve class is beta, and f of Pi is Zi, is in Zi, for I from 1 to n, where Zi are cycles with Poincare dual alpha I in cohomology theory of X with rational coefficients. So pictorially speaking, I have X, okay, and I have chosen sub-varieties of X. So I have chosen Z1, okay, I've chosen some other locus Z2, and I've chosen some other locus Zn, like that, and I'm looking at curves that are passing through this system, right? So I'm looking at curves that have point of intersection with these loci, and the points of intersections are exactly the markings that we have. And as soon as you give me a subvariety, it gives me a homology class. By Poincare that homology class. So Poincare dual of this homology class inside H lower star of XQ is our alpha I by definition. Okay, so this is making sure that algebraically speaking, we mathematicians, we construct a certain machine that rigorously defines this picture for us. We keep track of where the curve develops this singularity. Okay, so that's what we are doing. And yeah, and remember, I didn't say Zi's are elements of H2, H lower 2, H. I didn't say that because it depends. Maybe I want the curve to meet a line at some point, but to meet a surface at some other place, and to meet a point at some other place. These could be different degrees. They cannot just surpass the degree of the ambient variety, obviously. Right? Okay, so that's what it is. Okay.
So,
yeah.
Let me ask you stupid questions.
Go ahead. Your questions are very good. What?
So, do you have any good property for a title here? I'm not familiar with the intersection theory. So, in general, when we define an exception on push forward, we need the title should be good. In the homology theory in algebraic geometry, sometimes we need the title has some good smooth.
That's right.
That's our proper.
Yes, yes. You need that property also in here. But the fact that these are, so far we are doing this for non-singular projective convex varieties. So this pi actually does have that property. So you're right. You're right. Push forward is problematic.
Yeah, because here is an exceptional push forward.
Yes, yes, yes. That's right. It's exceptional push forward. That's right. Very, very good. Okay, so that's that. Now, this element of homology has a degree. So what did I do? I took cohomology classes in here, pulled them back to here, right? And then I pushed them forward in here, and I Poincare dualized, right? So this thing has a degree. Degree of the class, the Gromov-Witten class, Ig and beta, of the choice of n cohomology classes in X is equal to 2m plus sum of I from 1 to n degree of alpha i's, which is equal to 2m. This is the dimension, real dimension, dimension over real numbers of m bar g and x beta. As remember, right? So it's going to be 2 times g minus 1 times dimension of x, complex dimension of x, okay, plus 2 times integral over beta of canonical bundle of x, canonical class of x, plus sum 1 to n degree of alpha I. You might ask yourself, when is it that this homology class is not defined? Well, if it's degree 0, that means it's a point class, because this is a homology class. If it's degree 0, it means it's a point class. Okay, it's still defined, but negative degree certainly undefined, right? So Gromov-Witten class makes sense as far as this expression is positive or 0. If it is negative, it's not definable. Okay, so for instance, if genus is equal to 0, then this becomes a negative number. Better be that this compensates for this, okay? If genus is 0 and x is Calabi-Yau. If x is Calabi-Yau, remember, canonical bundle of x is a line bundle. It makes sense to ask, what's this? This is the degree of this line bundle over a curve with homology class beta. It's the degree of this, the definition of degree of a line bundle, basically, along a curve. Meaning, if you have a curve, if you look at the section of this line bundle, how many points this line bundle meets that curve, basically, okay? Or algebraic geometry. Think about this. Line bundles in algebraic geometry are divisors. These are hypersurfaces. If you have the hypersurface defined by the line bundle, k of x, that hypersurface, at how many points does it meet a curve with homology class beta? So you're looking at, this is a hypersurface, and this curve keeps hitting it. And this number is actually this number, how many times it hits it. If this hypersurface defined by the canonical bundle is in a way that when x is a Calabi-Yau, canonical bundle is O, that means it meets at 0 points. So if x is Calabi-Yau, this goes away, and if genus is 0, this is 0, and this is a negative number. Better be that you're fixing cohomology classes in a way that there's degrees sum to a positive number. Otherwise, your moduli space, your class of the set of curves passing through this many will be empty because its degree will be negative. So, right? So you know, you understand what's going on. Okay, nice. Gromov-Witten invariant. The Gromov-Witten invariant is I use the notation of bracket because it's a bracket between homology class you produce in here and a cohomology class. And so it's a bracket between, so it's a IgN beta alpha 1 to alpha n, which is integral, as far as it makes sense, over m bar gn of this class, IgN beta. You see how interesting this construction is? After all, the lab in which you compute your workstation is in here. Pull back a class in here, take n cohomology classes in here, pull it back in here, it spits out a certain element of cohomology. That certain element of cohomology basically tells you how to separate those curves that pass through these divisors. You push it down in here and then you integrate. Now you might ask, can I integrate on here too, just without pushing forward? The answer is yes. But the Gromov-Witten class lives in cohomology theory of M bar Gn. That's why this is well defined. So this is IGN beta alpha 1 to alpha n intersected with fundamental or virtual fundamental class of M bar Gn. If it is a smooth, you don't need to worry about virtual fundamental class because the tangent sheaf of that moduli space doesn't jump in dimension. So everything is flat. So this intersection number will stay constant as you roam around. But if it's not, you need to virtually look at not a whole space, but the part of the space in which the tangent sheaf is well defined as a bundle. As a bundle. Okay, so that's that. Okay. Beautiful, right? Beautiful subject. Do you agree? It's like a nice story. Okay, so as you see, I keep this picture because this is the most instructive thing, actually. Okay. So, whenever this is true, whenever expected dimension of M bar Gn, expected dimension over R, over real numbers of M bar Gn is equal to 2 times 3G minus 3 plus N. Okay? Otherwise, doesn't make sense. Again, you don't want moduli space M bar Gn itself to be empty. Okay, you're taking classes up there, but you see, this is really, really interesting, right? If you want to define some element in here, it better be landing on a non-empty locus. And then you can integrate against this thing, for which this thing should have some minimal allowable expected dimension. But as you can see, expected dimension of this space sees X and the map. It sees X. Expected dimension of this thing doesn't see X. There is no X. What X? Okay. So they have different dimensions. Okay. Now remark, here is the remark. Using pull back, push forward, formula, and the fact that pull back, push forward formula, and the fact that I, G, and beta of alpha 1 to alpha n is pi 2, defined as pi 2 lower shriek of pi 1 upper star of alpha 1 tensor to alpha n. Okay, we get that IGN beta of alpha 1 alpha n is defined as integral over M bar Gn x beta of the pullback of that thing. There's a pullback push forward formula that says if you take a class in here and push it down and integrate, you can relate it to integrating that class in here. That's the pushback, pull back, push forward formula. So you don't need to, in order for this number you calculate in here to be the same as this number, you need to use the Giessen push forward map, the way we just defined it. Anyway, I deleted it. Pi to lower strict. You don't need to do that as long as you pull back and just integrate. So even though a priori Gromov-Witten invariant is defined as an integral in here, the pullback push forward formula allows you to compute over there. But this is really fun because expected dimension of this thing might be different than this thing. So some of the restrictions this guy imposes on you in terms of the degree of the cohomology classes, you do not need to worry about when you're integrating in here. So even though Gromov-Witten class might not be defined if this number becomes negative, in here, that integral is still might make sense. So Gromov-Witten number, so far, I have said, whenever this number 3g minus 3 plus n is bigger than 0, bigger than or equal to 0, you can define a Gromov-Witten number. That's a huge restriction on what can be the g and what can be the n, right? But let's see what happens over there. Okay, so let's call this thing something. Star. Here's the remark. Star makes sense when n plus 2g is smaller than 3. It does make sense. However, IGN beta alpha 1 to alpha n makes sense only for n plus 2g bigger than or equal to 3. This tells us that even though Gromov-Witten class might not make sense for n plus 2g, yeah. Oh, I thought someone is talking to me. N plus 2g less than 3, the Gromov-Witten invariant, meaning the integral, makes sense for all g and n. So the Gromov-Witten invariant, for Gromov-Witten invariant, you don't need to necessarily construct Gromov-Witten class, because by push forward pull back formula we know that once I, g, and beta is defined, its integral here is equal to the integral pullback of classes over there. So Gromov-Witten invariants are defined for all genus and all number of mark points. But Gromov-Witten class is not. Whenever Gromov-Witten class is defined, then the Gromov-Witten invariance is equal to integral of the Gromov-Witten class over the moduli space of stable connected curves. Okay? This is the statement. That's why in Gromov-Witten theory, when you calculate Gromov-Witten invariance, you don't restrict n or g. All genus, all. And that's the original thing that physicists wanted, right? Because these are string world sheaves and develop all different kinds of shapes. Okay, good. now, so let me, good. So that, yeah, no, we have good time. All right, so this is this for all genus. So now I need to tell you why this number you integrate is a deformation invariant, right? So why should we care about deformation theory, deformation invariance? Well, because we are algebraic geometers and we are geometers and mathematicians, we like to define invariants associated to a space, even though the shape of the space keeps deforming. That's one answer. It's valuable, it's very nice, it's respectable point of view. The other point of view is that because this has a background in physics, and then these are string worldsheets, and the path of the strings develops different types of shapes. So we did stratify that integral. We cut it into pieces. We keep the topology of the path, but then there are infinitely many possible ways that this path can deform. Two reasons. One is that the strings themselves are wobbly objects. They are deforming as they are moving around. That's one. Second is that we are doing quantum gravity. Gravity is fluctuating, and the ambient space is undergoing infinitesimal deformations, both in terms of its complex structure, in terms of Kähler structure. So everything is just changing. So we would like to compute a number out of this highly wobbly picture. So both answers are valid and respectable. We make an assumption. Let us make an assumption that m bar gn x beta is a smooth orbifold of expected dimension. Now let me tell you one thing which is probably important. If you have a tangent sheaf, okay, and it becomes its dimension doesn't jump, the tangent sheaf itself becomes a vector bundle, that's the criteria for a smoothness, okay? So if H1 of that bundle, sheaf, H1 of tangent sheaf vanishes, for sure it's guaranteed that there's nothing else to worry about. It's all higher cohomology vanish. There's nothing else to worry about, so it's a bundle. There is something I want you to pay attention, which you might not even guess could be the possibility, but absolutely is, which is it's a sheaf. And you calculate its cohomology. It could be that this sheaf has higher cohomology, but its H0 makes a bundle. So you could be in a situation that you have a smooth space, but the obstruction sheaf on this space does not vanish. We call these things the smooth obstructed spaces. And why is it? Because it's a cohomology class that doesn't vanish. Nevertheless, its H0 also keeps being a bundle. So the way it is that if H1 vanishes, you're guaranteed the smoothness. But the smoothness does not guarantee H1 vanish. Okay, it's one way. All right. So you could have obstructed the smooth spaces. So if you go to a conference, you lecture, or whatever, you say this space is smooth and obstructed. What? I thought obstruction measures for missing element. No, it's not true. Obstruction is obstruction. It's a cohomology of a certain sheaf. It could exist. What measures for you the smoothness is looking at the deformation of space, just a tangent. If that tangent thing jumps in dimension, it's not as smooth. When obstruction vanishes, it doesn't jump. You know. Okay. Okay. Cotangent complex of a space, which we will discuss, measures how far are we from being smooth? The cotangent complex actually tells you, you look at the sheaf of Kähler differentials on a space. Cotangent bundle. Cotangent bundle is the differential forms, right? Sheaf of Kähler differentials is just a fancy algebraic name for differential forms. The sheaf of differential form, degree one differential one forms on the space. This thing might not be a bundle. If it is not a bundle, your space is non-smooth. Cotangent complex tells you that this thing has a resolution. So how far do I need to go in this resolution to get to a bundle? You might go very far, infinitely many degrees far, and you will still not get a bundle. Okay, so this cotangent sheaf of differentials, or cotangent sheaf, this thing actually, if it is locally free, meaning it's a bound bundle, then your space is smooth, otherwise it's not. It could be that it makes a bundle, but your space, the sheaf, the dual of this sheaf, tangent sheaf, has higher cohomologies. Could be. All right, there's a smooth example. We discussed about smooth stable map moduli spaces. This was M bar 0n PR D times class of P1 is a smooth, we discussed it, is a smooth orbifold of dimension R times D plus R plus D plus N minus 3. Okay, degree D lines in projective space. In full generality, when genus is bigger than or equal to 1, or genus equal to 0 and X is not PR, for most varieties, X dimension of M bar Gn X beta is bigger than expected dimension of M bar Gn X beta. Now you know why, because the dimension of this thing is the rank of the tangent bundle, right? Two-dimensional space, rank 2 bundle. Three-dimensional space, rank 3 bundle. Okay, but the expected dimension is the rank of tangent minus the obstruction, H0 minus H1. So it's always some number less than that. So this is saying that if the genus is bigger than 1, often this is not as smooth. Or if the genus is 0 and X is not projective space, it's also not as smooth. And so dimension of the space is bigger than expected dimension of this space. There is this Koronishi map, which takes you from H0 of the tangent sheaf to H1 of the tangent sheaf. You take the 0, point in there, look at the preimage of 0, and that gives you a locus inside this space with expected dimension. That map, by the way, is called Koronishi. Okay, so that. I still need this picture, so I keep it. Okay, so that's that. And so in general, this is not as smooth. To remedy this issue, and define Gromov-Witten invariants, we construct virtual fundamental class. Okay. All right. Recall that the Gromov-Witten invariant as an integral of the Gromov-Witten class is given by integral over m bar gn x beta, because of the pullback push forward formula of pullback of n-fold product of cohomology classes in X. We can rewrite this integral in terms of fundamental class. That's what it means anyway. Okay? So fundamental class m bar gn x beta lives in homology theory of m bar gn x beta with rational coefficients. For the smooth case, for the smooth orbifold case. So we can assume, let us make the assumption that this space is a smooth orbifold of expected dimension. Its examples are things like this, genus zero projective, or some other situations. But this is smooth. Very easily it fails to be smooth. That's the discussion here. So let us now define that integral. So fundamental cycle is defined here. And if I take m bar gn x beta, its Poincare dual. If I take the Poincare dual of this thing, dimension of this thing when it is smooth is the dimension of the whole space, right? It's the top degree homology class, right? When you dualize it, what's the codimension of the whole space? Zero, right? It's codimension 0, right? So the Poincare dual of this thing is degree 0 class in cohomology theory. So it is 1 constant H0 of m bar gn x beta. So at least when the space is smooth, this is true. Poincare duality works. You can take the Poincare dual and you land on a codimension 0 class, degree 0 cohomology class, and that's just constant numbers. You don't need to put 5 or 13 or 20, all of them are the same. Okay, it's constant. Okay, so if E is the dimension of this smooth space, then the Poincare duality map, we have the Poincare dualization, Poincare duality map. So Poincare duality takes you from H upper star of m bar gn x beta to H 2 times E minus a star. We work over real dimensions, right? Minus that, minus a star of m bar gn x beta with Q, which is defined by the cup product with fundamental class m bar gn x beta. So if you have a class in here, alpha, if you have a class in here, alpha gets mapped to alpha intersected with fundamental class of m bar gn x beta. Fundamental class of m bar gn x beta is sitting in degree H2E of the moduli space with rational coefficients, whatever degree of this thing is degree star, you will get an element in 2e minus a star because it's a cohomology degree. Okay? All right. So why is this actually useful? Because now look at what's happening in here, right? I'm assuming that this is a smooth. That finishes the lecture today. So let's define it. And then the rest we will do next time. So I can take pi 2 lower shriek of pi upper star of alpha 1 tensor alpha n. So that is going to be pi 2 lower shriek of Poincare dualization of pi 1 upper star of alpha 1, pi 1 upper star over 1 times alpha n cap with fundamental class of mgn x beta. Right? I start with cohomology class in here. I go up there. It's a smooth orbital, so Poincare duality works. I need to produce a class that this does give me this intersection. I Poincare dualize, and I then intersect with the virtual class. So this is going to be PD inverse of pi 2 PD inverse of pi 2 lower star of pi 1 upper star of that capped with m bar gn x beta. Good. Yes. And then this is going to be Poincare dual of P2 So now, so let's see. So I want to use this diagram. So this is m bar gn x beta goes to m bar gn times xn. This is the map pi 1 and pi 2, which is our map pi. Okay? And so I call this map pi, the tuple, like that. And then I have a map from here to m bar gn, and I have a map from here to xn. I call this thing P2, and I call this thing P1. And then, as you can see, I have the maps from m bar gn to here, and I have a map from m bar gn to here. This map I call pi 1. That map I call pi 2. All I did really is that I would like to use this map, which I want to call pi, the tuple of these two things. I want to use it, write everything with respect to that pi thing. Nothing fancy, really. So that. All right. So this is going to be P2 lowest. Okay, so I write it down here. So this is going to be Poincare dual inverse of P2 lower star of pi lower star of pi is, again, pi 1, pi 2 lower star. That's what pi is. Okay? Of pi upper star of P1 upper star of alpha 1 tensor alpha n capped with m bar gn x beta. Okay? That's what it is. And so result of this I write in here. So IGN. So this shows that IGN beta alpha 1 to alpha n is defined as PD inverse of P2 lower star of P1 upper star of alpha 1 tensor with alpha n capped with pi lower star of MGN x beta, which is Poincare dual of P2 lower star of P1 upper star alpha 1 times alpha n lower star of M bar GN x beta. Whenever n plus 2g is bigger than 3. So, why did I do that? Why did I do that, right? Kind of going such a, because I told you that this Gisin push forward has a particular definition involving Poincare dualization. There is no Gisin Schrick anymore here. So that's it. That's what pi 2 lower Schrick does. That's the definition. So now if you forget about all of those things and you just look at this diagram rather, you can understand what pi 2 lower Schrick is doing. Okay, so we are pulling back things in here to here and then pi 2 lower Schrick, but along the way we do Poincare dualizations. So we pull back, okay, so in this level, we pull back and we collapse it with fundamental cycle, okay? And then we write this pi 2 lower star. We use the commutativity of this diagram, basically, okay? So we rather pull back things to here rather, and then to here, and then push it forward to this product, and then via P2 send it to here. So what do? We pull back things to here first, right? Right? And then we pull back MGN x beta. We also have this thing. And then we collapse things with each other. And then we want to send it to here. So we push it forward to here, and then via P2 we send it down there. And along the way, we dualize these things because I would like to get this intersection. So I dualize it. And this Poincare dualization is right here. So now, as you can see, there are Poincare dualization in different levels. Here, originally, Poincare dualization was an M bar GN x beta, but because this space is a smooth, and I considered this to be a smooth space and a smooth space, I can think of not dualizing and then dualizing later after pushing down onto here. So the Poincare dualization here happens in the level of M bar GN, but here happens in the level of M bar GN x beta. Okay? So none of this could be the case if you didn't have a space with orbifold structure, which is fine. We still define Gromov-Witten invariants, at least on those spaces. Okay. Okay. So do I need to? Yeah, that's it. And then that's the Gromov-Witten class. Integral of this class against fundamental cycle of this gives you the Gromov-Witten invariant. Okay, so for this, I just wanted to, first of all, translate for you what pi 2 lower Schrick does. Second, translate for you how integral in here is realized as an integral in here. It's like that. Okay, thank you very much. See you next time, tomorrow. Yeah, 10 minutes beyond.